Last lecture, we looked at spin precession, so strong magnetic field in the z direction, and how the spin angular momentum would precess around that z direction. Today, we're going to continue on with our discussion of time evolution, but this time, rather than just limiting our field to the z direction, we're going to look at the magnetic field in an arbitrary direction. So just to summarize what we've done, if you recall, the general sort of way we go about looking at time evolution is we figure out what our Hamiltonian for the system is, that total energy operator, and we diagonalize that to determine the eigenvalues and eigenvectors. Once we have those, we then write whatever our initial state of our system is in that energy basis. So just a linear combination of all those energy eigenvectors. To get the time-dependent state vector, then we just have to include those extra phase factors that depend on the eigenvalues of that energy operator. And that gives us our time dependence of those coefficients of in that state vector. Once we have our state vector as a function of time, we can then calculate whatever probabilities or expectation values we're interested in. What we did last time is we looked at the a general superposition state of our spin 1/2 system. So it's in some superposition of spin up, spin down in this block sphere representation that is somewhere up at some angle defined by theta and phi. When we have our magnetic field in the z direction, that defined sort of our Hamiltonian as that magnetic moment dotted with that magnetic field vector. And what we saw was that these expectation values had these forms, and it amounted to this spin angular momentum vector rotating, precessing around that z-axis, the direction of our magnetic field, which was the axis that was defined by the eigenvalues of our Hamiltonian. And that is what we called spin precession. It maps sort of exactly to what you would expect in a semi-classical sense, where if you just had a magnetic moment vector pointed in some direction in a static magnetic field, that vector would precess about that magnetic field. So what if the magnetic field is not aligned with Z? What if, for example, we had two components to our magnetic field, one in the Z direction and one in the X direction. Now, you could obviously just redefine your coordinate system so that whatever direction that is in becomes your z direction and we get the same result. But just to keep things general, and because it does map to a lot of important problems and gets us a bit further than that simple case, we're going to stick with our XYZ coordinate system and say that our magnetic field is aligned in this direction. The Hamiltonian is then again just that negative magnetic moment dotted with that magnetic field. Our magnetic moment is E B over ME times that spin vector. So when we take that dot product, we get this in terms of the spin in the X direction and spin in the Z direction. Or if we want to write that in terms of angular velocities or angular frequencies, rather, we can just make those substitutions. And we have our Hamiltonian looks like that. Since we know our spin operators, our S sub x is just ones on the off diagonal, or times h bar over 2, and our S sub z is h bar over 2 times 1 and negative 1 along the diagonal. This Hamiltonian in the z basis matrix representation looks like this. So we figured out, the same way we did last time, what our Hamiltonian is. Now, the first step in figuring out our time dependence is just diagonalize this. So to diagonalize a 2 by 2 Hamiltonian, we just take the determinant of our secular equation, the Hamiltonian minus our eigenvalues times the identity matrix, and set that equal to 0. So that looks like this. If we take that determinant, we get the diagonal terms multiplied with each other minus the off diagonal terms multiplied with each other. Going through all that algebra, in the diagonal terms, when they multiply with each other, those cross terms the h bar omega 0 over 2 times lambda cancels with the other cross term. So we end up with that, and you can see that the eigenvalues for our Hamiltonian are h bar over 2 squared times square root omega naught squared plus omega 1 squared. Rather than continue on with our typical diagonalization sort of formula and thing we learned in linear algebra and that, we're going to simplify this Hamiltonian a bit using some trig. And we'll see why in a minute. But essentially, if you look at the magnetic field we've applied, we have that B0 in the z direction and B1 in the x direction to give our total magnetic field vector. If we just look at those triangles, we can see that, sine theta is opposite over hypotenuse, the opposite having a magnitude of b1, the hypotenuse being, b1 squared plus b0 squared all square rooted. Likewise, cosine would be the same thing, but be, adjacent over hypotenuse. So we have these two identities, and since, the angular frequencies we've been writing these field strengths as are just linearly proportional to that, we can actually make the substitution, and all of the E over mass of the electrons will cancel. And we have that sine theta is equal to omega 1 over square root omega naught, omega 0 t squared plus omega 1 squared. And similarly for the cosine theta, which allows us to write omega naught and omega 1 in this form. With those sort of identities coming from this trig, we can rewrite the Hamiltonian we derived in terms of these sine cosine terms, right? We can factor out that square root term, and we have this as our Hamiltonian. Now, once we have this, we can look back at some things we discussed earlier when we were looking at a magnetic field, or not a magnetic field, when we were looking at the spin components in a general direction n, we had this spin sub n operator, and we looked at the eigenvalues of those. Now, in this case, if we define that n direction as the direction of our magnetic field, this phi is 0. So those e to the I phi terms are just 1. We can get rid of them, and we see that our Hamiltonian that we've just rewritten can be written in terms of that s sub n operator. And we have that. And since that Hamiltonian, by definition, since it's proportional to the s sub n operator, since those commute, they share eigenvectors. So we don't have to actually go through the whole solution again. We know they share common eigenvectors. So our eigenvector for the higher energy or E plus state is just the spin up in the n direction, and likewise for the E minus or spin down in the n direction states. Again, previously when we derived these eigenvectors, they were e to the I phi terms. Phi is 0 in this case, so they go to 1. So now we've kind of got through the first step of solving time-dependent problems. We have the eigenvalues and eigenvectors for our Hamiltonian. Now it's a matter of writing the initial state in terms of those eigenvectors, and then adding the phase factors and seeing what we get. So let's look at an example, the typical one where at t equals 0, we are in a state that is spin up in the z direction, right? If we want to expand that state in terms of our energy eigenbasis, all we're really doing is we're multiplying by the identity matrix. And if you recall, that identity matrix can be rewritten, thanks to completeness, as just the sum of all the outer products in that basis. So in this case, it's going to be the spin up in the n direction, ket and bra outer product, plus the spin down in the n direction, ket and bra, acting on that initial state, which was our spin up in the z direction state. Now, we can then take those inner products when we bring in that spin up state inside that brackets. And if we want to calculate those inner products, well, spin up in the n direction, inner product with spin up in the z direction we need to write them in the same bases. We know them both in the z bases, so we'll write them that way. And you can see that the plus plus term is equal to 1, the minus plus term is 0 because that's an orthonormal basis. So we get the inner products, those two inner products end up being cosine theta over 2 and sine theta over 2. What that all means, putting it together, the state vector at t equals 0 can be rewritten as cosine theta over 2 spin up in the n direction plus sine theta over 2 spin down in the n direction. Once we have that, the next step is to add the phase factors for each of those coefficients. So we take those exponentials, e to the minus I, energy of that eigenvector, t over h bar. Likewise for the other one, where, as we've derived before, those eigenvalues or those energies are plus or minus h bar over 2 square root omega 0 squared plus omega 1 squared. So the last thing to do is then calculate the probabilities later on that we're interested in. So let's look at the probability of measuring spin down in the z direction at some later time t, keeping in mind that we started in the spin up in the z direction. Well, we're going to use postulate 4 to look at that probability. It's just that inner product squared. Writing that in terms of the time-dependent state vector gives us this, where we've written it in terms of the energy eigenbases, bringing in that spin down bra, we get these inner products. And just like we did previously, we can calculate those inner products just by writing them in the same bases and taking the coefficients that are non-zero. And we end up with this. Spin down in the z direction, inner product with spin up in the n direction gives us sine theta over 2. And similarly, for the spin down in the z direction, inner product with spin down in the n direction gives us negative cosine theta over 2. So plugging those values in, we get this. We get the probability of measuring a spin down at some time t is equal to cosine squared theta over 2 sine squared theta over 2 times the magnitude of that difference of exponentials, all squared. This can be simplified, right? So if we use these two trig identities, a double angle formula in sine, as well as the exponential way of writing the sine of x, we can make those substitutions. The cos squared, sine squared term outside the magnitude there becomes sine squared theta all over 4, and inside that magnitude squared term is 2i sine of that whole parentheses there. That simplifies a bit more. The h bars cancel. The 2i ends up becoming a 4 that cancels the other 4. And we end up with the probability of measuring a spin down at some later time t is sine squared theta sine squared omega naught squared plus omega 1 squared, all square rooted over 2 times t. We can simplify this even a little further by thinking back to our trig identities when we were looking at the magnetic field we were applying. Recall sine of theta is just opposite over hypotenuse, which we showed we could write as omega 1 divided by the 2 omegas added in quadrature, all square rooted. So that sine squared theta can be rewritten as omega 1 squared over omega naught 0 squared plus omega 1 squared, giving us what is known as Rabi's formula, shown here. And it's the probability of measuring a spin flip at some later time t. We have a spin up in the z direction. We have a magnetic field that is not aligned in the z direction, and that spin will oscillate, and eventually you'll see some probability of measuring a spin down. So let's look at a case. Let's say B0 equals 0. So we actually don't have a magnetic field in the z direction. We only have that x component. Well, that means that our energy eigenbases would be that spin in the x direction, that plus or spin up or spin down in the x direction. So that sort of defines what I like to think of as the axis our Hamiltonian is in this block sphere representation. Now, Rabi's formula gives us this and lets us know what the probability of measuring a spin down at some time t would be. Taking omega is not equal to 0 gives us this. That simplifies things quite a bit. And it looks like we have that probability is going to oscillate between 1 and 0. This is, in the block sphere representation, the exact same sort of picture we looked at last time of spin precession. We're using different axes now, where start with some spin up in the z direction state vector. We have a magnetic field defined in the x direction that sort of sets our Hamiltonian, and that spin up state vector starts to precess around that magnetic field direction, and we just get it, precessing around our block sphere like this, and the probabilities oscillate from 0% of us measuring a spin down in the z direction when the state vector is up here, all the way down to up to 1 of unity probability of measuring spin down when the state vector is pointing here, and just oscillating around like that, precessing at a frequency defined by frequency omega 1 that's set by the strength of that magnetic field in the x direction. So what about another example? Both the z and the x fields are on. We'll say the magnetic field in the z direction is larger than that in the x direction. Doesn't even have to be extremely larger, but bigger in this case. Well, that magnetic field is going to be pointed off at some angle theta, as we showed. That describes the axes of our energy basis eigenvectors. So we're going to have some spin in that n direction vectors that define that axes that are the energy eigenstates of our Hamiltonian. We start with some initial state vector pointed in the spin up in the z direction state, and that probability oscillates according to the Rabi's formula. Now, since omega 1 and omega 0 are both non-zero, what we see is this probability oscillates with an amplitude that is less than 1. The probability that we measure a spin down at some later time is never going to become unity. It can be 0, but it can't be unity because it's a sine squared function times some number less than 1. What does this mean? How do we think about this? Well, essentially, it's going to look like this. That probability of measuring a spin down is going to oscillate with this sine squared term, but the amplitude is going to be less than 1. So we're going to see the same sort of oscillations in probability, but not as large amplitude. This, in this block sphere representation, is again much like what we saw with spin precession, except for the state vector starts in the z direction, and our Hamiltonian sort of axis is defined off at some angle theta, and that state vector just precesses around the axis defined by the energy eigenstates of our Hamiltonian. If B in the z direction is much larger than B in the x direction, that oscillation frequency is going to be approximately the one defined by that strong z field. But again, very similar to the spin precession case that we saw previously, where we just have a spin rotating around some axes defined by our Hamiltonian energy eigenstates. You may be asking yourself, well, this seemed a little more complicated than our previous example. What's the benefit of not just redefining our z-axis in the direction of the magnetic field? And it turns out that this Rabi's formula in general, but this whole method of analysis maps well beyond to systems way beyond our simple spin 1/2 system. It's used in quantum computation a lot. Essentially, quantum computation involves using what are called qubits, which is where this sort of block sphere representation comes from, where qubits are any two-level system. So you take any quantum mechanical system that has a two-dimensional Hilbert space, and you can map that to these sort of dynamics, where you can have voltages you're applying to your experiment, and by changing a voltage, you change the Hamiltonian, so you change what those energy eigenstates are, and then you're going to start to see this precession. If you were in an energy eigenstate at the start, then you quickly pulsed to a different Hamiltonian. Well, that state's no longer in an eigenstate. It's in a superposition, and you're going to see these Rabi oscillations as it precesses around the axes defined by those new energy eigenstates. The book walks through in nice detail the example of neutrino oscillations, where you can have an electron and a muon neutrinos, and essentially they discuss how there's two different um, Hamiltonians for the system. One, when they're in the nucleus, and there's that weak force interaction between them, so that defines one Hamiltonian. Then after the decay, there is a different Hamiltonian because there's no longer that weak force interaction. It's just what they call the mass eigenstates, or what the energy eigenstates are. And so you have two different bases, and both of those define to describe an energy eigenbasis depending on where you are in this process. So if you start as, say, an electron neutrino, once that decays and you end up in a new Hamiltonian where that weak force is gone, you're no longer in an energy eigenstate, and you're going to see these Rabi oscillations between those two different neutrino uh, masses. The book goes through that in detail. It's an interesting read. I am not a particle physicist or high energy physicist by any means, so they will clarify any misspeaking I may have just done there. It's hard to overstate how broad this sort of analysis can apply to. Like I said, any two-level system in quantum mechanics can sort of map to this spin 1/2 system. So very useful. It's also this Rabi, this general analysis we did now is going to be very useful when in our next video when we go to time-dependent Hamiltonians. So not a static magnetic field at some direction, but a magnetic field we're actually changing with time.